Hi everyone, this is Abhinav. A few weeks back, I wrote this long article on virtual memory. It's almost 25,000 words and 60 pages in PDF format. It has been received really well. I think many of you like the new format of a dialogue based explanation. Uh, and many of you have also purchased a PDF, and I really appreciate the support. Um, so But I also understand that this sort of format is not for everyone. So many people prefer more direct to the point explanations. Uh, so I wanted to do that. So I decided that I'll make a series of short videos covering the same set of topics, but instead of doing story based coverage, I would do more crisper, more direct explanations. But again, following the same first principles exploration of the every topic that I talk about. So in that series, this is the going to be the first video. In this video, we are going to be talking about what is virtual memory, why do we need it, and why should we care about it. Um, so so instead of giving you that same textbook definition, I'll start with the first principle explanation. So we'll go to the bottom, start from the problem that exists for which virtual memory was designed. And once we understand that problem, virtual memory will automatically emerge as the obvious solution. And once that solution, you connect those dots, everything above that layer, every other aspect of virtual memory will also start to make sense. So let's start to talk about that problem. So virtual memory is very strongly tied to our programming model because at the end of the day, it is how we access memory in our code. Um, so, so in modern days, when we write code, we are writing code in higher level languages like Java, Python, JavaScript, Rust, and in those languages, we have a lot of abstraction between our code and the hardware. So we have compiler, we have the runtime, we have even the operating system, which is managing the memory for us. So we usually don't care about how do we access, how the memory looks like. So let's go to a bare metal model where none of these abstractions exist. So only hardware and our code exists. So let's assume we have a very simple hardware um, with a very small amount of memory. Let's say 8 bytes of memory. So one, two, three, four, five, six. Now, so P1. So I'll name these addresses. These are the physical memory addresses. So this is physical memory. Um, and so here we don't have a compiler, we don't have an assembler, no runtime, not even an operating system. And let's also assume that here only one program can run at a time. So if we are writing a program, we can assume that only our process will be running when it executes on that system. So if for such a system, if you had to write a program, let's say a simple program like this, which stores value 10 into memory, 12 into memory, and then does something like adds them together and writes the result back into memory. So if you were writing code in a higher level languages, a compiler would have translated it into machine instruction, but here we have to do that ourselves. So uh, so if you think about it, what does this mean? So a is equal to 10. We are saying that we want to store the value somewhere in memory. uh, a compiler or a runtime would have associated a with an address in memory. Here that job is left to us, so we have to allocate memory. And here, because we know that when this program executes, only our only that process will be executing, so we can freely use any of these available 8 addresses in memory. So because no one else will be using that at that time, so we can if we are writing the machine code ourselves, so if we are writing the machine instructions, write 10, we can hard code the address P1 itself. Similarly, for storing 12, we can hard code the address in the program itself. So the binary itself has the physical addresses hard coded. So when the hardware starts to execute, it will simply write 10 into the physical address P1. Uh, this is all safe because only one program is running. But in real world, in today's time, we have machines where hundreds of processes run in parallel, either due to multi-core or because the operating system does context switching. So it executes one process, then switches to another, executes that, and so on. So all these processes which are running concurrently, they are sharing the same limited amount of physical memory. So you can think like four processes are running at the same time, uh, and each using some amount of physical memory. So this approach, the way I showed here, where physical addresses are hard coded in the program code itself, that approach will not work because P1 at the time of execution might be in use by another process. So this approach is not really viable. Um, so so this is the problem. We want to be able to execute several processes concurrently, all of them sharing the same limited amount of physical memory, but safely. At the same time, also efficiently. So we don't want the processes to be contending, like figuring out what addresses are safe to use. So it has to be fast at the same time safe. So how do we solve that? So that is the problem. So in computer science, there is a famous saying that every problem can be solved by one layer of indirection. So if we add one layer of indirection between our code and the physical memory, that would solve this problem. So what that means is that if we have a layer in here, uh, um, I'll just draw it here. Let me start again. So I'll draw it more cleanly. So so now let's what we need is one layer of indirection. So we have our physical memory. Um, so P1, P2, P3, P4, and so on. Now we are adding one layer of indirection, which is uh, virtual memory. This also has addresses, so we are calling it V1, V2, V3, V4, V5, V6, V7, so on. Um, so um, so now so basically, let me first. So this is called virtual memory, which means it is virtual. It means that it does not really exist in the physical reality. So it's memory which is uh, in a software abstraction which is mimicking physical memory. So it has addresses. You can uh, read and write these addresses, but in physical reality, there is nothing like that. So it's all implemented in software with some help from the hardware.